So good morning, everyone. Welcome today to the CMCC webinar. I'm Dorotea Iovino, scientist in the other division at CMCC. And it's a pleasure today to introduce Enrico Scoccimarro and give his space for his research with the talk and the seminar that is going to be on the role of typhoon in drying of maritime continents. But before giving the word and the floor to Enrico, I would like to spend a few minutes for introducing the CMCC. So the Air Mediterranean Center on Climate Change is a non-profit research organization that was established in 2005, and 10 years after it became a foundation, so in 2015. Our research, as suggested by the name, focuses on understanding the climate variability and understanding the impact of this variability on the environment, the society, the business world. One of our main goals is to further understand the different components of the health system, and also to promote and to facilitate the interplay between scientists, decision makers, and also try to raise awareness among a more general public. So our work also aims to, of course, protect the environment, develop a strategy for adaptation and mitigation of climate change, and to stimulate sustainable growth. The research center is organized as a network of 9 different research divisions. They are distributed through the country, through Italy, going from the south in Lecce, where also the central administration is located, to Bologna, where both Enrico and I work, and further north to Milan and Venice. This network connects public and private entities that collaborate with the aim of enhancing, as I said, interdisciplinary, and try to connect the different aspects of climate science. The research division that you have on this slide listed share different knowledge and different scientific skill, going from computer science for the support needed for our numerical tools, so the management of data, to division that works more on numerical modeling of the atmosphere, the ocean, or land. And then to division that are more involved in understanding the impacts of climate change and of studying the climate risk, analyze those, and make adaptation strategy. There are, of course, many topics that our research can cover. You can go through the CMCC webpage, where you will have more details. You will have news on our last results and our activities. To conclude, of course, our scientific results are disseminated through scientific papers, peer-reviewed papers. We have technical reports describing our tools and our implementation. But CMCC is also highly engaged in educational program, or in organizing and participating to communication events and activities for a generic public. After the seminar, or during the seminar, you of course can ask questions to Enrico. You have, if you go to the GoToWebinar control panel, that should be on the right side of your screen. You can post questions there. And then I will ask them to Enrico in the end. So before going to Enrico's seminar, I will spend another few minutes to introduce him and his research. Enrico Scoccimarro is a senior scientist at CMCC within the climate simulation and prediction division. He boasts 20 years of experience in climate modeling, focusing mainly on processes coupling the atmosphere with the ocean. He has contributed to develop and to implement several climate models during his career. And also, of course, he has used them to perform climate scenario simulation and projection. He is highly involved in participating into the CMIP exercise from phase 3 to the most recent phase 6. And of course, his data or data that he produces are also used for the IPCC reports. Enrico has participated to several international projects as the European H2020 program, mainly contributing to high-resolution numerical modeling, but also study with the particularly interested extreme events. In this field, of course, his interest goes to tropical cyclones and the interaction of the cyclones with the climate system. He is a member of the TCMIP, the Tropical Cyclone Modeling and Comparison Project. He is also a member of the US Climate Hurricane Working Group since 2011. He also participated as a member to the European Marine Board Expert Group for the definition of the strategic research agenda for the ocean and human health for the European sites. And since this year, he is a member of the Management Committee of the European Work for Mediterranean Cyclone in Weather and Climate. He has a bunch of publications and is always keen to participate to international conferences, and more than half of his work is actually focused on cyclone. So Enrico, if you want to start, you're absolutely welcome.
Okay, thank you very much, Dorotea. Let me try to share the screen. So, did you give me the screen? Show my screen.
Yes, I do.
Okay. Okay. So, can you see the first slide? Dorotea,
yes.
Can you see the first? Okay, so let me start. Good morning, everybody. First of all, let me thank Dorotea for the introduction and all of you for being here today. We are going to talk about the research work that we have done here in CESP, the Climate Simulation and Prediction Division of the CMCC, as part of our research line activity on tropical cyclones. In particular, today we will deeply discuss the evaluation of tropical cyclone role in modulating the amount of water available for precipitation over the maritime continent. Here's the outline of the talk today. We will first briefly introduce the atmospheric process object of this study. We'll just touch on tropical cyclone formation, domain of interest, and main associated impacts. And then we will spend a few words on the tropical cyclone research activity at CMCC, the tools we build on, the fully coupled general circulation model, and how good they are in representing the tropical cyclone. We will then focus on the tropical cyclone modulation of the water amount available for precipitation over a particular portion of the equatorial domain, the maritime continent. And you know, and this is something that we will also mention in a few slides, that one of the most important impacts induced by TC typically is the one related to the associated floods. And this is also due to the extreme precipitation associated, but in this study, we highlight for the first time an opposite behavior, that is the tropical cyclone impact in terms of drying of a portion of the tropical domain. We'll then spend a few slides on data and methods, then the description of the result, the discussion, and finally we will just summarize the main finding. A tropical cyclone is one of the most damaging natural forces on Earth, getting energy from the ocean and developing over the tropical warm water and traveling along the basin, also hitting the coast in some cases. Favorable environmental conditions for tropical cyclone development are warm ocean water, so this has to be true not only for the surface but also for the first 50 meters of depth. And also it is important to have an atmosphere that cools fast enough in the vertical in a way to result potentially unstable to moist convection. Also, relatively most air near the mid-level of the troposphere is required, and generally a minimum distance of about 500 kilometers from the equator is necessary to have a sufficiently high Coriolis force to maintain the process. Also, pre-existing near-surface disturbance are required, and low level of vertical wind shear are preferred because this is facilitating the formation of the towers. The nomenclature of tropical cyclone is basin dependent, with their most intense classes higher than 33 meters per second, that corresponds to about 100 kilometers per hour, are named hurricanes in the North Atlantic and Eastern Pacific, and typhoon in the West North Pacific. Instead, the term intense tropical cyclone is used in the southern hemisphere to represent their strong manifestation. So from a physical point of view, the hurricanes and the typhoon are the same thing, just strong tropical cyclone. And there are 5 categories to classify hurricanes and typhoon once they reach the 33 meters per second wind velocity at the surface. And these classes are defined based on the Saffir-Simpson scale, with the strongest class, the category 5-1, associated to winds higher than 70 meters per second, corresponding to more than 220 kilometers per hour. There are about 90 tropical cyclones per year at the global scale, with most of them located in the Northwest Pacific, the domain we are going to investigate, where also the most intense and large ones are located. Tropical cyclone season is the warm one, so from June to November in the Northern Hemisphere and from October to May in the Southern Hemisphere. As previously anticipated, some of the storms can reach the coast and have severe impacts, mainly in terms of strong winds associated to the storm surge induced by the wind pushing the ocean water inland, and extreme precipitation. These effects, this tropical cyclone-induced impact contributes to the annual worldwide damage of the order of billions of dollars and death toll of thousands of people. In the exercise of attribution of death to tropical cyclone, and we are here referring just to the Atlantic Ocean one, but this can also give us the flavor of the different contribution of the different impact. The extreme precipitation covers about 30% of the cases. So for this reason, the precipitation directly associated to the tropical cyclone has been the object of many analyses in the past. But now in this work, the idea is to try to focus on the opposite role that tropical cyclones can have, showing how they can contribute to the drying of a particular portion of the tropical domain, such as the Maritime Continent. Here you have the fraction of the precipitation associated to the tropical cyclone activity at the global scale as resulting from 30 years of historical observed data. These are data from the Global Precipitation Climatology Project, with some regions where you can see that the tropical cyclone fraction is more than 40%. It is evident that there is no direct contribution by tropical cyclones to the equatorial domain, as you can see here, and also over the Maritime Continent, there is no direct contribution of tropical cyclones to the precipitation. But since the circulation over this part of the tropics is fundamental for the global atmospheric dynamics, we wanted to check if there is some second-order effect of the tropical cyclone developing in the Western Pacific, so over all of this region here, over the Maritime Continent. Moving to the CMCC activity in terms of tropical cyclone research, we will just mention few steps. We started to investigate the relationship between the tropical cyclone and the climate system since the beginning of the creation of the CMCC consortium, when we started to participate to the couple model intercomparison project, as Dorotea already mentioned. At that time, we were in the symmetry phase, useful for the provision of data to the 4th assessment report of the Intergovernmental Panel on Climate Change. The possibility to investigate tropical cyclone and climate was due to the high resolution at that time of our model. That was one of the models with the highest resolution. It was about 110 kilometers, and it was already able to represent tropical cyclone better than many other general circulation models participating to the CMIP 3. So we then increased the resolution. In the next steps, we went to 80 kilometers in the CMIP 5 for the CMIP 5 effort, and then the actual CMIP 6 version of our model has in its higher resolution version the ability to represent category 5 tropical cyclones. So actually, of the more than 100 models participating to the CMIP 6 effort, only 3 are able to represent category 5 tropical cyclones, and one of these is the CMCC CM2 VHR4, one of the 2 models we are going to use in this work to corroborate our results. Here's the representation of the tropical cyclone genesis point as from the observation based on tracks coming from the hybrid track dataset for the 1970 to 1999, and this is what the models are able to do. This is just one of the different versions of the model we use. And just to say that also at low resolution, the genesis point is reasonably well represented by general circulation model. But then, if you are interested in the intensity of the tropical cyclone, we need to go to the 1/4 degree resolution of the last version of our model to be able to represent category 5 hurricanes. At this resolution, despite the
I think there are some connection problems. Dorotea, can you hear Enrico?
No, actually, I lost him during the movie.
Yes, exactly. Same here. Probably it's very heavy. So
We
Enrico,
can wait and see. He's
yes.
back after this.
Okay, he's trying to change the internet line.
Non mi senti, Dorotea?
Now, yes, now we can hear you.
No, okay, now you can hear me.
Yes, during the movies on your slides, probably they were very heavy on the line, and so we lost you.
Okay, let's keep the movie.
Yeah.
Okay, so in the movie, I was just showing that the model is able to represent very intense tropical cyclones, and also the interaction with the ocean is reasonably well captured. And this is another important feature of our general circulation model, because this can help in better represent the sea surface temperature negative feedback on tropical cyclones and give us the possibility to investigate the relationship with the ocean. Well, I spent few time on the description of general circulation models, and this is because we are going to use them also for the present analysis. Let's now focus on the Western Pacific tropical cyclone and the Maritime Continent. For this analysis, we build on 6-hourly tropical cyclone track information from the Japan Meteorological Agency. We are using daily precipitation data from the GPCP project, and also JRA 55 reanalysis. The Japanese reanalysis were also used to obtain the vertical integrated water transport component. This is also done at the daily time scale. We computed the transport level by level in the model, multiplying the specific humidity with the components of the velocity to obtain the zonal and meridional component, and then we computed the vertical integral. The data are collected for the period 1979 to 2015 for the summer season, defined as June to August months. The same parameters, the precipitation and the water transport, are also collected from two different versions of our CMCC CM2 model, the fully coupled version of our CMCC model. And these two versions share the same 1/4 degree resolution ocean, but the HR4 low resolution model has about 100 kilometers in the atmospheric component, and the other one, the VHR model, has 25 kilometers in its atmospheric component. In addition, on the model side, we also had to track tropical cyclone, as this has been done based on and this is necessary because if you want to track tropical cyclones, we need to add several fields in our analysis. We had to provide 6-hourly data for the relative vorticity, the maximum wind, the sea level pressure, and the temperature along the vertical to identify tropical cyclone condition and to follow them in the model output. To characterize the tropical cyclone activity on each June to August season, year by year, over the Western Pacific domain, we computed one of the diagnostics typically used to represent the tropical cyclone activity, that is the accumulated cyclone energy, ACE. This is a standard parameter that is taking into account tropical cyclone count, intensity, and duration in the basin, since this is resulting from the time integral of the square of the maximum velocity over all of the 6 hourly time steps of a tropical cyclone in the basin from June to August for that season. So the June to August ACE yearly time series are then used in two ways. The first one is to correlate this index representative of the tropical cyclone activity over the whole basin with time series of the June to August precipitation patterns. The second is to stratify the 1979-2015 period in two subsamples of equal length, one corresponding to high ACE value and the other one corresponding to low ACE values. This is better represented here, where the median of the time series is used to define the two subsamples characterizing high ACE years and low ACE years. The meteorological parameter will be then averaged over the two subsamples, and then we will take the difference between high and low to compare water transport and precipitation fields. This will give us a measure of the difference associated to a more active tropical cyclone season on the aforementioned parameters. Moving on to the results, here you have just to have a measure of the dependency on the horizontal resolution of the model ability to represent the tropical cyclone, the observational distribution of tropical cyclone jet energy points in the westport North Pacific in the upper left panel, and this is compared to low central panel and high lower panel model results. The low resolution model cannot represent both the tropical cyclone position and also the accumulated cyclone energy observed. This is the box plot obtained over 30-year period for observation in the two models, and you can see that only the very high resolution model at 25 kilometers horizontal resolution is able to reasonably represent the accumulated cyclone energy observed. Well, this map shows the correlation between the accumulated cyclone energy over the whole basin, season by season, over the period, and grid point by grid point precipitation time series averaged over the same June to August season. This is something that we obtained from the JRA 55 analysis, but the pattern is reasonably consistent with the GPCP observation, and it emerged that where the tropical cyclones are supposed to develop, the north of 5 degrees north, this region here, the correlation is positive with the red pattern showing positive correlation. But then, if we focus on the Maritime Continent at low latitude, you can see that the correlation results negative and significant. So this is suggesting that we can have less precipitation here over the Maritime Continent during year with particularly high tropical cyclone activity. This is also made evident putting together the ACE and the corresponding mean precipitation averaged over the two red and blue boxes. As you can see here, high ACE is associated to high precipitation in the red box and low precipitation in the blue box. Red pattern is clear and consistent with literature, but the blue pattern must be explained, and this is something that we are going to focus in the next slide. Another way to show this behavior is to stratify the precipitation following the procedure I described in the method section, stratifying over high ACE years and low ACE years based on the median of the 37 JJA values, and then compute the difference of the result in precipitation average. This is what we obtained, and this is showing red patterns indicating more precipitation associated to the high tropical cyclone activity, and blue pattern indicating less precipitation associated to the high tropical cyclone activity. These numbers in magnitude are more or less 30% of the climatological value we expect over the region. This is also clear if we compare Bloch's plot of precipitation averaged over the blue box separately corresponding for low and high ACE years. And in another way, we can take a look at the basin Y ACE corresponding to years when the maritime precipitation is low or high. This second series of Bloch plot here. So both these representations are confirming less precipitation over the maritime associated to more active tropical cyclone season in the West North Pacific. Well, there are many factors at play in the tropics that might have an effect on both tropical cyclone activity in the Western Pacific and on precipitation over the maritime continent. So we decided to investigate the found relationship in different contexts, also to verify if it is true that tropical cyclones are the responsible of the less precipitation over the maritime continent during particularly active years. And the different actors that could play a role are El Niño Southern Oscillation, the Manuel and Julian Oscillation, the Pacific-Japan pattern, and also the Hadley cell position and intensity. So as a first step, we computed the high minus low ACE precipitation pattern using ENSO neutral year only. So just 20 years of the 37 considering, excluding La Nina and El Nino years. This is what we obtained performing the same analysis, and the red pattern is still there, and also the blue pattern is still there over the maritime continent and significant, suggesting that the maritime precipitation correlation with the tropical cyclone activity is not dependent on El Niño Southern Oscillation. In addition, we also do a similar analysis for the different actors that we considered in the previous slide. And well, when we try to verify differences in the precipitation, stratifying result on, for instance, only inactive MJU years or negative or positive phases of the Pacific-Japan pattern, or also during different phases of the Hadley cell intersect and intensity index, while the relationship between the maritime precipitation and the West North Pacific ACE is still there, independently on all of these patterns of variability. So more precipitation is found where ACE is low, and less precipitation is found when ACE is high over the West North Pacific basin. In addition, to further reinforce the direct link between the tropical cyclone activity and the precipitation over the maritime continent, and also to verify the independency of the relationship from external modes of variability, we tried to focus on daily values, focusing on single season, as in this case, where you see the 2002 JJA season. This is the difference between precipitation stratified over tropical cyclone active days with respect to tropical cyclone inactive days. So this is just to say that the signal is still there also within the single season. And if you consider that there are about 50% of days over JJA in the Western Pacific associated to a tropical cyclone active and 50% associated to a non-active tropical cyclone. So this is somehow something that we can use to confirm that the signal is robust and also evident within the single season. This has been done not only for the 2002, but also for many other seasons, and the signal is still there. So the next step is to understand the mechanism behind. Here again on the left map, the well-known correlation between the ACE and the precipitation I have shown you at the beginning, together with a schematic representation of a tropical cyclone developing over the region in terms of expected associated water transport. This is better highlighted in the right map here, where the Lagrangian anomaly of the zonal water transport associated to a tropical cyclone developing in the Northwest Pacific is shown. And this is consistent with the associated wind direction. These are values vertically integrated of zonal water transport. The resulting induced zonal water transport is in the upper part of the storm domain westward, blue pattern, this direction here, negative, while in the equatorial part is eastward, the red pattern here. And this is what we can expect from a cyclonic circulation, because this transport is dominated by the wind that are eastward in the southern part of the domain. The western transport negative in the upper band is the one you can see here in the blue pattern, and the eastward transport, the red pattern here. And this is something that you can put on the map just to have an idea of the dimension of the process. The width of the domain subject to the eastward transport in the equatorial band, so the domain associated to this part of the transport, is of the order of thousands of kilometers and reaches the whole maritime continent when considering in particular the tropical cyclone traveling in these regions centered at about 10 degrees north. This is the same schematic representation, but over the map of the differences in precipitation associated to the high and low ACE years instead of the correlation you have seen before. And we claim here that such eastward tropical cyclone induced eastward transport is responsible for the reduction of the water available for precipitation over this region here, the Maritime Continent, causing the reduction of the precipitation during years with very active tropical cyclone season. And in fact, when you look at the differences, computed in the same way, stratifying in the same way, but in this case, the zonal water transport instead of the precipitation, you can see that during high, very active tropical cyclone years, there is a more pronounced and significant eastward water transport associated, and the difference in the amount of the precipitation between the high and the low ACE year is consistent with the difference in the zonal water transport over the region. And this is also consistent with the amount of water that is transported eastward by the southern flank of the tropical cyclones. If you count them, we consider all of the one traveling at around 10 degrees north. So on the left here, once again, the anomaly induced by the tropical cyclone on the zonal water transport, and this is again the composite over the high ACE years, and on the right, the difference of such transport integrated between the high and the low ACE years. The quantified difference in the amount of water transported eastward at low latitude by the tropical cyclone is quantitatively consistent with the less water precipitating over the Maritime Continent during high ACE years. Now, this is what we obtained based on the observation, but we also wanted to corroborate our results looking at our models, using our models as a tool. On the left here, you still have the representation of the difference in the precipitation associated to the high and low ACE years. And on the right, the result coming from the two models I mentioned. So the low resolution one in the upper panel, 100 kilometers of resolution, and the high resolution model, the lower one. So only the model able to realistically represent tropical cyclone can reproduce the process we mentioned, and we investigated looking at the observations. And this is consistent with the corresponding pattern of the differences of the zonal water transport. Only the high resolution model is able to represent the eastward, more pronounced eastward transport associated to very active tropical cyclone years, and the low resolution model is not able to represent this pattern. In addition, we also ran an experiment with the high resolution model, the CMCC CM2VHR4, the one with 25 kilometer resolution in the atmosphere, to verify if even within the single season we can confirm our hypothesis. So we identified the most tropical cyclone active month in the time series over the Western Pacific, and then we rerun the model for that month, starting from the same initial condition, but inhibiting the tropical cyclone development, putting to zero the evaporation flux over the domain where the tropical cyclone tends to develop and at the time in which it tends to start to develop. This is something that we can do working on the coupling interface between the atmosphere and the ocean, and this is something that gave us the possibility to compare the precipitation pattern and all of the parameters we are interested in the two simulations, the one with the tropical cyclone and the other one without the tropical cyclone, over what we expected to be a very active tropical cyclone season. So comparing the average precipitation in the two experiments, these are the results, and you can see that the experiment with the tropical cyclone free to develop tend to show more precipitation between 8 and 20 degrees north, where the tropical cyclone are expected to develop, and less precipitation is expected in the southern flank, where the tropical cyclone tend to reduce the water availability through the eastward water transport. This is somehow confirming our finding and was possible really thanks to the state-of-the-art general circulation model, finally able to represent even the most intense tropical cyclone. So just to summarize, the general circulation model can be used to understand the relationship between the tropical cyclone and the climate system, and while there is no direct contribution of tropical cyclone to the precipitation over the equatorial region, we demonstrated here that the tropical cyclone can play a role in the reduction of water available for precipitation at low latitude, as in the case of the Maritime Continent. This is something that we have corroborated also using modeling results, and what we would like to do in the future is to try to investigate if this process can also affect the onset of ENSO over the Maritime Continent, and we will try to investigate the potential role of the tropical cyclone in being a source of predictability in the onset of El Niño Southern oscillation. I think I can stop here. Dorotea, I think you have to get the floor.
Thanks a lot, Enrico.
Here a series of references. If you will download the presentation, you will have the possibility to find all of the paper mentioned.
Yeah, sure. So presentation will be actually available on the CMCC website, but also through the CMCC YouTube channel. So the video and the audio will be actually there. There are some questions, Enrico, so I'm going to start with those. The first is actually coming from me. Since I'm moderating, I'm asking my question before. And the question is relating to the ocean modeling. So for having, I mean, you using climate models, and how relevant is having a good high resolution and with good physics ocean component into the system for a realistic representation of the tropical cyclones?
Well, this is a really important point. I mean, in the past, we didn't have the feeling that the high resolution in the ocean was that important, because since we had low classes only represented in our general circulation modeling, the atmospheric component, because of the resolution of the atmospheric part of the system, we didn't have the feeling of the importance of the high resolution in the ocean, because the high resolution in the ocean comes useful to well represent the negative feedback that there is at the surface between the tropical cyclone and the ocean. So that at a certain point, the water diverging at the surface, we had the movie, but we lost it for some reason. The divergence of the water at the surface induced by the wind associated to the tropical cyclone, tends to recall cold water from below, and this is something cooling the surface, and this is having a role in reducing the magnitude of the intensity of the tropical cyclone itself. So it is a self-induced reduction of the intensity of the storm. And this is something that can be represented in high-resolution models with high resolution in both component atmosphere and ocean. And also it is really important, because if you run a high-resolution atmospheric model without this effect, so without a dynamical ocean coupled with them, you lose this effect, and the tropical storm can be, I have the slide, I think somewhere, I can show you. This is having an impact in terms of tropical cyclone intensity representation of the order of 70%. So let me say it better. If you simulate at the high frequency, at the high horizontal resolution tropical cyclone in a general circulation model without the ocean dynamically coupled below, you overestimate the intensity of the tropical cyclone in terms of power dissipation index. The power dissipation index is another index used to verify to quantify the energy associated to the disease, of the order of 70%. So instead, if you couple with the high frequency, the atmosphere to the ocean with a sufficiently high resolution in both components, you can reduce this overestimation of the intensity of the disease by 70% to 7%. And this is a really interesting result, suggesting that, well, having a couple ocean below is really important for the investigation also of the intensification of the storm, and this is true and valid also for the forecast at different time scales during the intensification of the cyclone, and also for a good representation of potential and investigation of potential changes in long-term simulation at the long-term time scale.
Thanks, Enrico. The second question, I'm going to read it. So it's how tropical and subtropical climate zone are interacting, informing continental climate and weather's precipitation. Is there any evidence of change effect caused by climate change and inversions?
So I'm not sure I got really well the point, but in general, the tropical cyclone have a role in the transport of, for instance, of moist from the tropical region to the exotropics, and also they have a role in the modulation of the oceanic transport. We have also worked, there is something here, yes, this is a slide related to this point. We verified that the tropical, and this was also possible thanks to our general circulation model, the tropical cyclone have a role in modulating the meridional transport of heat in the ocean, and this is something that can play a role in the modulation of the climate at the higher latitude. And in terms of climate change signal associated to tropical cyclone activity, and what we can say is that there is a tendency, and this is something coming from common experiment we have done also together with the US climate people, but also with our more than a single experiment, we can say that we do expect for the future less storms, which is because the atmosphere starts to be more stable than in the past. But together with this tendency to less tropical cyclones, we are going to have more intense disease because the energy available in the ocean starts to be more. And so when they start to develop, they can reach higher intensity. And also in terms of their latitudinal distribution, we can say that there is a reasonable significant signal in terms of their of the motion of the average position in latitude at higher latitude with respect to the past in the future scenario, especially in the RCP 8.5, the most intense scenario we tend to consider. Hope I answered.
Thank you, Enrico. Next question is actually on the tracking of TC based on the climate model outputs. So you have shown that there are many parameters that you have to define for set the TC condition. So the question is, that's for the high frequency. So if you want to have 6 hours, for example, the question is this kind of post-processing really consuming in space and time? And well, actually yes. The second part, sorry, I'm going to make 2 in once. The second part is there any different approach on the developments for the tracking of TC?
Okay, so yes, we need in order to track tropical cyclone in our models, we need to have a series of fields at the high time frequency, 6 hourly at least. And you know, this is a huge amount of data. We are talking about hundreds of terabytes of data for our analysis, and we need the 3-dimensional fields for instance, for the temperature, for the wind, and this is something really not that much consuming in terms of CPU time, but really we really need a lot of space on this to do our analysis, and this is something that, well, it is a bit tricky. There are actually some approaches, different approaches to try to track tropical cyclones from general circulation model output and also reanalysis. These are simplified methods, just looking, for instance, at two-dimensional fields, and this is something that is at the beginning of the development, so we still have not that good results compared to what we obtained, also taking into account the vertical structure of the storm and so on and so forth. But one step more that we want to do is, and there is also people already working on this, is to try to track tropical cyclone directly online in the model during the evolution of the computation, just to avoid the necessity to then save high frequency data over all of the levels of the model, just looking directly in the model in running time where you have a condition that could be attributed to a tropical cyclone. This is another approach that is evolving, and also there are exercises in the field of artificial intelligence, but again, we are at the beginning of the process, and we will see what it will happen in the few next years.
Okay, the last one, Enrico, is kind of more general. If there are any chemical aspects in studying the typhoon, or you just focus on the physical aspect and statistical modeling?
Well, yes, this is something that I have never done. I've never focused on chemical aspect of tropical cyclones. Sorry.
Okay, so I guess it's time to stop. So thanks for the question. If there are, I mean, there are more actually that we have no time to go through, but again, you can have more details if you want to relook the Enrico seminar. The webinar will be available online. And before leaving you for the lunch, I can go sharing again my screen. If I understand where, here I go. I just leave you with advertising the next CMCC webinar. There will be in a week from now, so it's 26th of May into the early afternoon. Giulia Caragi is going to present her scientific results, and the seminar will be moderated by Nadia Pinardi. So again, Enrico, thanks. And thanks for attending to all the participants.
Thank you all.
Enjoy the rest of the day. Bye-bye.
Bye-bye.